Buenas tardes.
Buenas tardes, profe.
¿Cómo están todos?
Ahí, más o menos.
Espero que no perdiendo peso.
Al contrario,
Al contrario, engordando todo el mundo.
apunte pan, profe, apunte pan.
A punta de pan.
Sí,
Ajá. Bueno, pero digamos no pueden pedir pollo y pizza a domicilio.
no, creo, o sea, creo que vi que algunos restaurantes sí, pero no todos.
Aquí somos un montón, ¿no? Somos como 15 estudiantes. Vamos a ver, esperar que se anoten un poco más.
Profe, una pregunta, para lo que toca enviar el documento a Evelyn de la tesis, toca mandarle con la firma escaneada, ¿no es cierto?
Sí, puedes mandarla o si tienes electrónica, puedes firmarla electrónicamente. Si no, con la firma escaneada está bien.
Y no sabe cómo saco la firma electrónica.
¿Cómo qué?
¿Cómo hago la firma electrónica?
Ah, la firma electrónica sí es un proceso, ¿no? Si ya no lo tienes, no es momento, no es momento para obtenerla. Eso tiene que hacer un proceso con la alcaldía o la gobernación. Hay una oficina a la que tienes que acudir para que registrar esa firma, que la dan en un CD, un pendrive y entonces la puedes usar de ahí. Pero eso es una cosa más oficial, ¿no? No
Claro,
basta con generarla con Acrobat simplemente.
claro, claro.
Sería bueno que los estudiantes todos se sacaran su firma electrónica porque eso facilita muchas cosas. Ustedes saben que toda la documentación pública o tiene que hacerla electrónica o tiene que hacerla física, ¿no? No puedes hacer una mezcla. Entonces,
Claro.
por ahora están permitiendo mezclas sobre todo para estas presentaciones de tesis que están haciendo ahora virtuales. En principio todas se tenían que ser físicas o todas electrónicas, pero entonces los estudiantes no tienen firma electrónica y entonces han tenido que hacer resoluciones especiales para poder hacer las defensas virtuales, ¿no?
Ya. Pero medio feo, medio loro hacer eso, así, la defensa virtual, ¿no?
Medio feo. Bueno, en física nosotros preguntamos a todos los estudiantes y nadie quiso hacer defensa virtual hasta ahora. Los químicos aparentemente sí están haciendo, los matemáticos, pero claro, te pierdes todo el evento social con tu familia y todas esas cosas, ¿no? Así
Claro.
que no es lo mejor. Bueno, si se pueden aplazar, porque digamos la graduación estaba pautada para mediados de abril y ya creo que eso va a tener que moverse la fecha, ¿no? Entonces,
Pero no
este,
no le han dicho si es que se van a postergar algo el calendario.
sí, acaba de salir una resolución hoy sobre todas las libertades que se dan a la hora a las instituciones para adaptarnos a la situación o sea, adaptar el semestre a la situación que está presentada, ¿no? Entonces, me imagino que usaremos todas esas herramientas. Por ejemplo, permiten esto de tener firmas virtuales y firmas físicas en el mismo documento y ese tipo de cosas, ¿no? Entonces, vamos a analizar eso bien y ya, por ejemplo, dieron permiso para extender el semestre hasta un 25% más de tiempo, que me parece, no sé si es apropiado, porque los laboratorios, todos los que vamos a tener que hacer después que salgamos de la emergencia.
Claro,
Y bueno, pero podemos tener por ejemplo, permiten hacer laboratorios virtuales, este, y eso quizás lo podemos implementar bien en el tronco común, ¿no? Que se pueden hacer estas demostraciones o hacer simulaciones en línea con los estudiantes y este tipo de cosas. Los laboratorios de la carrera sí es algo más difícil que tenemos que pensar cómo hacer.
claro, eso sí, en todo común, pero acá se complica porque no es estaba pensando cómo es el laboratorio así.
Ujú. Sí, ese es el principal problema, sí.
Profe, por
Bueno,
ejemplo, ¿cuáles son las libertades que ustedes tienen? ¿Hasta qué punto llegan esas libertades?
bueno, eso están todos, acabo de leerme el documento por encima y entonces lo que hacen es que dejan a la institución un poco dentro de lo que llaman la autonomía responsable. Sobre todo, o sea, el objetivo es garantizarles a ustedes el derecho a la educación, ¿no? Entonces, eh, podemos, digamos, repensar toda un poco la manera de impartir clases, la manera de evaluar, todas estas cosas están susceptibles de poder ser cambiadas por la institución, por ejemplo, los retiros se flexibilizan también. Eh, el documento se lo pasamos a los representantes estudiantiles. Eso acaba de llegarme ahorita hace unos minutos, pues estaba leyéndolo antes de la clase. Entonces tenemos que analizar eso, a ver qué libertades tenemos. Lo que sí recuerda es que las extensiones de semestre son del 25% nada más, ¿no? Entonces, ese parece ser un número un poco más duro que fijó el CES. Este, pero de resto yo creo que tenemos bastante flexibilidad. Yo creo que por lo menos dentro de este curso eh, eh, yo creo que cada curso hay que pensar cómo se manejan lo de los laboratorios. En este curso yo creo que algunas prácticas se pueden hacer este, quizás con alguna modalidad virtual y dejar entonces un grupo de prácticas para hacerlo hands-on cuando regresemos, ¿no? Entonces, si podemos hacer uso de los espacios de los estudiantes de Common Core, que los hagan por estas modalidades virtuales, entonces vamos a tener, tú sabes, semanas enteras seguidas dedicadas a hacer las prácticas, a cumplir con las prácticas de las distintas materias. Yo creo que esa sería la mejor opción, ¿no? De manera de reducir al mínimo lo que se pueda las prácticas hands-on, si se puede, si no se puede, bueno, entonces estarán las prácticas enteras hands-on asociadas con, con la etapa cuando regresemos, y si no, bueno, que se hagan un mínimo de prácticas de laboratorio. Y bueno, eso también, todo esto de común acuerdo, pues también ustedes son como evaluadores de la calidad del semestre. Entonces, yo creo que todo esto tenemos que hacerlo en discusión con ustedes. La parte teórica son, digamos, mucho más sencilla. Quizás ahorita en este periodo deberíamos abocarnos a cubrir bien la parte teórica y ver cómo, por ejemplo, si podemos modificar las evaluaciones si es que no pensamos que se puede hacer un midterm como estaba planeado, por ejemplo, hacer más énfasis en las tareas, cambiar los porcentajes de esas evaluaciones y de mutuo acuerdo con ustedes, ¿no? Lleguemos a un acuerdo de qué es lo que es la calidad mínima que queremos para el curso, para cada uno de los cursos. Yo pienso que la modalidad que tenemos nosotros de darle un peso alto a las tareas, que es un trabajo individual que tienen que ser más o menos individual y grupo que tienen que hacer ustedes, y tengamos sesiones prácticas sustanciales para que, digamos, el aislamiento no les provoque una desventaja para rendir en este tipo de cosas, pero de resto mantener el nivel de las tareas y de la parte teórica del curso, ¿no? Así que cualquier cosa que quieran discutir, digamos, al respecto de la estructura de los cursos, de proposiciones que tengan, y yo creo que cada profesor tiene que tomarla en cuenta y actuar correspondientemente con eso, ¿no? ¿De acuerdo? ¿Alguna otra comentario, pregunta. Ok, ya tenemos, bueno, ya tenemos, we have 11 students now, 10 students online. If you know anybody else who might be sort of, you think might not be in contact for some reason, or maybe you can send a message or something, whether they will be joining us in this session. Otherwise, of course, as always, we're going to record this, so anybody not present can access the class afterwards. Okay. Everybody has been able to access the video classes that I posted. I mean, any problem with this? They're not very large. I mean, the largest I think is about 140 megabytes. So I think you can. It's not difficult to see after class. Okay, so let's begin here. So I have here the whiteboard. Okay, so this as much as possible. Let's see the size of the pen. Okay. Okay, so last time we were talking about degenerate semiconductors. Okay, so degenerate semiconductors. Okay, so I basically am mentioning degenerate semiconductors because we're not we're not going to consider this case, and this case so to distinguish this case from the one we're treating mostly in this course is that we're going to always we will always consider the dilute impurity limit. Okay. In the dilute impurity limit, it's reasonable to consider that we have either donor levels, which are a very, very thin band, okay, close to the conduction band, or a very, very thin band of acceptor levels, okay, acceptor levels, which will be close to the valence band. Okay, so this is the dilute limit. So no impurity interaction. Impurity interaction. Okay, if there's no impurity interaction, we have basically the sum of the individual impurity levels, and that's what we draw here. Okay, so in the degenerate case, okay, we have then that we have again the conduction and valence bands. Okay, but as the impurities interact, then they don't have they're not just a set of levels, but they're a band, and this band may overlap, okay, with the conduction band. So we can have something like this, overlapping like this. Okay, and this will be essentially a metal. Okay, so this is not what we want. We're trying to describe a semiconductor. This would be, okay, bands, okay, overlap, and we would have a metal. We have a metal. Okay, okay, not what we want. Okay, so we won't be addressing this degenerate case. So I just wanted to point out so that you're clear that we're always in the dilute impurity limit, so that this is the scenario that we're going to address. Okay. Okay. Any questions about this? Okay. So now we want to address the impurity level occupation. Okay, so as we discussed before, it is much easier to ionize the impurities versus the process in which we relocate an electron from the valence band to the conduction band. So if we have impurity levels like this, it's much easier to pay this ionization energy, okay? Because we know that these energies are of the order of 10 milli-electron volts, depending on the substrate, okay? If you have the substrate as silicon and then you dope it with phosphor, or if you have the substrate is silicon and you dope with a boron, okay? This is also going to be of the order of 10 milli-electron volts. So this is comparable, okay? Comparable to the KBT, okay? Comparable to KBT at room temperature. Okay, we always remember that this is 25 milli-electron volts. So it's very easy to ionize these impurities. So for example, in the donor case, you would have one excess electron here. So this electron gets transferred to the conduction band. So you have a minus charge here, and then you leave the donor with a plus charge, or you can promote electrons to the boron, for example, in silicon. So now you get a negative charge here, and you get a positive hole here. Okay, let me put this in, circle this so you can distinguish it from the energy levels. Okay, so at room temperature, whatever impurities I have, either donors or acceptors, those will provide the carriers, dominating over, paying the whole, the gap energy in order to generate carriers from the electrons that are in the valence band, okay? Conduction band. Okay? So, so this is the idea. So now we want to make this ionization, or the contributions from the ionized donors and acceptors, we want to make this quantitative, okay? So let's calculate, okay? So always, let me just remind once more, non-degenerate limit. Okay, so we're going to calculate the mean number of electrons in an impurity state. Okay, so let's use something that you learned with Alejandro. So what are the occupations? So I have a particular impurity level, okay, an impurity level. Okay, and this level can be in 3 different states, okay? So the first state is unoccupied. This is a state, okay? That means it has no electrons, okay? The second state can be that it can be singly occupied, okay? With either spin up or spin down, okay? And then the third situation can be doubly occupied. That is both at the same time, okay? So here we should put or, okay? Doubly occupied, okay? So we had both up and down spins, okay? So in this course, we will always consider this to be energetically costly. Okay, why? Because there's a Coulomb interaction here. Coulomb interaction. Okay, so we will consider that this is not taking into account. So we only have either an unoccupied impurity or a singly occupied impurity. Okay, so we discard this case so that we can now compute the mean number. Okay, so we compute the mean occupation number of that impurity. Occupation, mean occupation number of impurity. Okay, and this is going to be the sum over impurity levels, okay, or the sum of the occupation, okay, so this is a sum over states, okay, of the impurity level, and then we have e to the minus beta, the impurity level energy, okay, minus the Fermi energy, okay, and this we divide by the same sum, but omitting the n here, so we just have the partition function, which will be this. Okay, so notice that this will be the this Fermi energy here is going to be the Fermi energy of all the donor states, all donor, okay, or acceptor, right? States. So let me just illustrate this for the donor states only. Okay. So EF is going to be the total number, okay, the number of the occupation number times the individual, okay, so this will be the chemical potential. So this is like the Fermi energy per particle, okay, okay, of Fermi energy per particle. So we're treating each impurity separately, okay? So let's now execute this sum exactly, so you know exactly what I mean, what I'm meaning with each of these symbols. So in the first case, we had a zero occupation, okay? So this will be 0 times e to the minus beta, and this will be 0 energy, okay, minus 0 times the chemical potential, okay, per particle. Okay, that would be the first term in the sum. Then we would have 1 occupation, okay, and this would be e to the minus beta. And then we would have energy associated with the donor. Let me put like a small an epsilon. Okay, so this would be the donor energy, okay, minus one particle that has a chemical potential mu, okay, so this is a product, okay, and this would be the spin up case. And then we have the other case where we have the spin down case. So this is 1 times this exactly the same because we have no spin, no energies associated to spin. So this would be the spin down case. Okay, we put it here so that you don't get confused with the notation. And then we ignore the third term. Okay, so the double occupation we ignore from this sum. This is essentially saying that we exclude it from the sum. And then the bottom sum, okay, as we do not have this 0 in the bottom sum because we don't have this number here, this would be just 1. So this exponential is equal to 1. So this is 1 plus, and now we add these two terms. So we have 2 e to the minus beta. Okay, so that will be the sum. So completing this procedure here, so we have now only just the 2 term, the term that's twice e to the beta e sub d minus mu divided by 1 plus 2 e to the minus beta. Okay, so that would be it. Okay, so that would be, so this is the average number of electrons that are on a single impurity. Okay, average number in the case of a donor, average number of E's on impurity. Okay, is this clear? Any questions about this? Okay, so generally in the literature, this is written like this. So this result is written like this. So you have the average occupation of an impurity is, so I pass the 2 to the denominator. Okay, so we get 1 plus 1/2, okay, of e to the minus epsilon sub b minus b. Okay, so if we want now the total density, so this is for a single impurity. Okay, but we have a total. Now we call the density of impurities, we call it big D. Okay, this will be the density of impurities, donor impurities in this case, in solid, okay, or in crystal. Okay, so in order to obtain the density of electrons on impurities, we have to multiply then the total number of impurities times the average occupation of each. Okay, so this is more or less the impurities are only half filled. For example, they have 1 electron, or they have half an electron on average. We multiply by the total number of impurities, either ionized or not, okay, in the solid, and we get the expression for the average occupation. The density of electrons on impurities. Okay, so this will be like this. Is this clear? Okay, so we have this expression here. Here, maybe this factor here is sort of rather strange from maybe the exercises you did in statistical mechanics. And generally, this 1/2 factor is taken to be sort of an adjustable parameter. Okay, so I think they call this 1/g or something like this. Okay, strictly from this derivation, it should be a 2, but then they take this as an adjustable parameter. So maybe for silicon, it's going to be something a little less than 1/2, or for germanium, it's going to be a little larger than 1/2, okay? Because this is sort of a very simple model for the occupation of impurities. And you'll see all the problems that are involved in the occupation of an impurity in the solids. We will see that shortly, okay? But sort of this is the strict result of the model, and but then you will see in the literature that this prefactor may change depending on the base material which you dope, okay, with a particular impurity. Another very easy way to see, to denote, to calculate this total density of occupied impurities, okay, or the charge that is on the impurity and not in the conduction or the valence band, okay. So this will be again the same. This is the same as this one, okay. Will be to start from the total number of impurities, the total number of impurity atoms, okay, minus the number of impurity atoms which are ionized, okay. This will be number of impurity, okay. This could be phosphor, okay, impurity atoms that are ionized, okay. So this is another way to calculate this. If you know the number of ionized impurities, obviously the density will be the density associated with the remaining electrons. Here we don't have these impurities are ionized, so they lost their electrons. So the total amount of impurities less those that are ionized are the ones that are the charges left on impurities. Okay, charges. This will be charges left on impurities. Okay, so this is one quantity we need to know about. Okay, when we for the following steps we're going to do, which is to apply the condition of charge neutrality that we know must be satisfied in order to determine the full concentrations of carriers either in the conduction or the valence band. Any questions with this? So of course, we could have done the same derivation for the positive carriers in the valence band. So we have now positive charges associated with the acceptor impurities. This will be the total density of acceptor atoms and the same factor that we know. Okay, so that will be the analogous expression for the acceptor atoms. Okay. Okay, so now let's consider the general case. General case. In the general case, we have both dope. We have both impurities are going to donate. So donating impurities, impurities that donate electrons, and we also have acceptors. Okay. So if we have both simultaneously, then what happens? Okay. So if we have both, sorry. I'm writing blue now. If we have both donors and acceptors. Okay, and this concept of donors and acceptors is actually a little more general than one might think. We don't always have to have, for example, a foreign atom coming into a matrix in order to be a donor or an acceptor. For example, a defect in the crystal may act as a donor or as an acceptor. Okay, so this can be also the effect of having a dislocation or having a missing atom in the lattice can act in the same way as donors as acceptors are, and acceptors are. So for now we think of them as impurities, but they can be more general in nature. Okay. So when we have both donors and acceptors, we have the compensation phenomenon. Compensation. Okay, and this this is a concept here. Okay, so compensation is that many of these donors, for example, and this is maybe the origin of this concept is associated to the fact that when we have the conduction and valence bands, okay, so in principle we have a few levels here and maybe just a couple of levels here. So these electrons, these electrons can go from here to the conduction band, but some of these electrons can also go down here to the holes that are present in these impurities. So you see that one type of impurities compensates the other type of impurities. Okay, so now these impurities will not be available for them to be occupied by electrons that come from the valence band. Okay. Okay, we can even have the situation where the compensation is complete. So we have as many donor levels as we have acceptor levels. So that will be a completely compensated semiconductor, okay? And we will see that those types of semiconductors behave like an intrinsic semiconductor from many points of view, although we will have many a different concentration of impurities because they won't all the carriers will not be intrinsic carriers. Okay, so this is the phenomenon of compensation. So from this comes the language of N-type. Okay, so we have N-type semiconductor. The N-type semiconductor is just the semiconductor where we have more donors than acceptors, okay? And the P-type. So maybe before I gave you the idea that the N-type has exclusively donor impurities, but no, this is not the case. So the concept is extended so to when the donor impurities are dominant over the acceptor impurities, and the other way around for the P-type semiconductors. Okay, so this is just a very simple extension, and of course we have so both of these are partially compensated semiconductors, and we also have the situation of fully compensated semiconductors. Okay, so we have ND is equal to NA. Okay, you know what compensate means in English? Compensate. Okay, this is, for example, if you do something against someone else, okay, so this you do some injustice to someone, okay, so you have to compensate him. So you either go to jail or you give him money, right? So this is a compensation. Okay, so this is why, in this sense, it's So here, the injustice would be including just donor impurity. So you compensate the semiconductor by including some acceptor impurity. Okay, so this is the sense the sense in which this word is being used in this context. Okay. Okay, so let's go to the full picture now here. So let me try to draw this a little bit with some technical expertise. Let's see, use the ruler here. So let me draw here a line. Let me draw so let me use the full view graph for this picture here. So you have the conduction band, okay, and the valence band, and then I'm going to draw here a few levels with different color. Okay, so we have the impurity levels here. This is the doping levels, the donor levels, I mean, and then we have the acceptor levels here. Okay, and the other things I'll draw freehand. Okay, so we can eliminate this. So again, we go back to black. So we have here the conduction band, the valence band, okay, and we have the donor levels and the acceptor levels, okay? So look at all the scenarios we're going to have. So here I'm going to call the total density of electrons, or carriers, in the conduction band, I'm going to call N0. And the total density of holes in the valence band, I'm going to call P0, okay? So this is going to be the density from whatever source, okay? So let's suppose here that we're going to have ionized. So these are going to be the ionized donors. So each of these, now we can choose another color here. So we're going to have all these donors here are going to be ionized, okay? Here, maybe we choose a couple which are going to be compensating, okay? And here we would have, these will be all the ionized acceptor levels, okay? And these will be the ones that are compensated, okay? So let's put, let's put it with the same convention as above, okay? Then the other ones, I'm going to leave none in black. Okay, I'm making lots of artistic judgments here. So non-ionized, okay, and these will be all the ionized donors and acceptors, of course, okay. Okay, so this will be the case. So we now have, for each of these electrons here, we will have, for each of those ionized impurities, we're going to have electrons up here, okay? And we're going to have positive charges down here. Okay? These won't be ionized, so these are neutral because they haven't separated themselves from their electron. their excess electrons. So these would be phosphor atoms, for example, in silicon. And these won't have an excess negative charge because they stay with their positive, with their hole in the electronic structure. Okay. What is missing from here? We also will have additional charges here because we will have now some positive charges here and some negative charges here associated with intrinsic. Okay, so this will be intrinsic holes and intrinsic electrons. Okay, so this is the full picture. So these are compensated. Okay, so these are impurities that are ionized by compensation. So these impurities lose their electrons, and these electrons fall into the holes. So this is one process that can happen. Then we can have electrons being transferred by thermal. Okay, thermal. Okay, and thermal. Yes, any questions? Yes? No? Okay, so this is the full scenario here. Let me put here, okay, ED. I have anything else that I have to draw on here? No. Okay, so remember this is the total hole concentration, and this is the total electron concentration. Okay, so this counts the electrons coming either from the intrinsic thermal electrons or from the impurities, okay? And we will miss here these electrons due to the impurities that, in spite of them being ionized, they don't go to the conduction band, but they go down to the acceptor levels, okay? And here the same thing. The total number of holes, be they from impurities or from thermal fluctuations, and this would take into account the fact that we don't get any holes from these impurities being ionized because they are ionized by compensation. Okay, so this is sort of the process called compensation here. Okay, so is this clear? Of course, I'm calling here thermal intrinsic. Okay. Intrinsic just means that these electrons are coming from the silicon itself, okay? It's assume, okay? Assume that silicon is the matrix, okay? Silicon is matrix, okay? So this would be, for example, phosphor levels, and this would be boron levels, okay? And then, okay, we can have of course, all these carriers are always coming from thermal processes, but the thermal process involved for ionizing, which is this process here, ionization, has a much lower cost in energy than this. But anyway, we'll have a very small tail. These are much less probable. Okay, so this will be associated with the intrinsic electron concentration. So this we will denote by this, due to this very small process here that is going to be much smaller than these carriers, okay? But remember also that we are in the dilute limit, okay? So there are so many carriers that we can ionize here, okay? And while there's lots and lots of carriers that we can ionize from the silicon, okay, separating electrons from the silicon. So, for example, in the very high energy limit, very high temperature limit, we can ionize many more intrinsic carriers than we can ionize the impurity carriers. Okay, is this clear? Anyway, we will go back to those concepts again. Okay, so let's put down here now the neutrality condition. Okay, this is going to be very important, okay, because we know that all the atoms, okay, all the atoms that compose this structure are going to be neutral originally, right? So if they're neutral originally, then no matter, as long as we don't add electrons, okay, or subtract electrons from the solid, then we must always obey this neutrality condition. Okay? So let's see how we write this in an equation, okay? So the equation would be, so total number of E's, okay, negative charges would be equal to the total number of holes. Okay? So how do we write this? Then what are the total number of electrons here in the conduction band? Well, it's N0. This is the total number of electrons in the conduction band. So that would be N0. Okay? What other source do we have of negative charges? Okay? All the negative charges that are in the acceptor level. So all the electrons in the conduction band will be negative charges. All the negative charges in the acceptor levels will be negative charges. So this will be the ionized acceptor levels. And this is going to be equal to the total number of holes in the conduction band. These are going to be all positive charges, okay, from whatever source, okay, plus the number of donor levels that are ionized, all the positive charges that are here, okay? So this is minus all the minus charges and all the plus charges. Is this clear? So this is the neutrality condition, okay? Okay, so from this, if this is clear, then we can use those relations and the previous relations that we obtained. So from the relationship, the total density of positive charges in the acceptor levels are going to be, okay, we wrote this one before, or the corresponding for the doping. So this is going to be the total number of acceptor levels minus the total number of acceptor levels that are ionized, okay? I put a minus sign. Okay, because it's a charge negatively, okay? And so this implies that Na is going to be equal to the total density of acceptors minus P. Okay? The same for the density of electrons in donor levels is going to be Nd minus Nd plus. Okay, so this implies that Nd plus is going to be Nd minus. Okay. Oh, good. So we developed a few relationships here, and now we're going to go back to the relation. So equilibrium. So let's derive a relation, which is the equilibrium concentration of carriers. Okay. So here we have, we're starting with the previous relationship that we had before, the condition of neutrality. So we have N0, the total density in the conduction band, plus the total of acceptor with negative charges is going to be the total density of holes in the valence band, plus the total number of negative positive charges on the donor levels. Okay? So we can write this in another way. So using these relations above, we have N0 plus, okay, number of acceptors minus PA. This would be N minus from here. And this will be N0 plus the number donors, total number of donors, minus the charges remaining in the unionized donor. Okay? So one approximation we can make, okay? So assumption, in room temperature, okay? At room temperature, and we'll see what the limits of these approximations are shortly, okay? Is that all the impurity, the donor atoms will be ionized, okay? So this means that this is 0, okay? And all the acceptors will be ionized, so this will be also. That means that we have no remaining acceptors that are not occupied by electrons from the valence band, and no donor levels that have let go of their electrons. So these two quantities are 0. So we end up, okay, we end up with this relation here. Any questions about this? Okay, so this is very important. This is a very important assumption. Immediately we're going to see how it can go wrong, or what is the limits of that assumption. Okay, but we have this relationship here. Okay, now we invoke the mass action relation. Okay. We also remember that this is with the Maxwell-Boltzmann approximation. Okay. So this is one problem with the treatment of semiconductors. There are many hidden assumptions that you make, that you have to make. You have to make you make in order to simplify the expressions, but you have to be aware of these assumptions that you make, so that you don't run into the wrong territory. Okay, so the mass action relation, and let me put this in the following graph. So mass action was the following result. Remember that we had that P0 times N0 was equal to N intrinsic squared, okay? This is in the Maxwell-Boltzmann approximation, okay? But remember that this relationship did not depend on the Fermi level, okay? So this was valid, okay? Valid also for doped, for the doped case. Okay? So we assume that, so let's substitute that into our equation. So we have N0 plus Na. Okay, it's important to follow these derivations, because we're going to, many of the equations, when we have non-equilibrium situations, are going to depend on differential equations that tell you how this variation is going to, how these densities are going to vary in time. Okay. So it's good, it's important that we understand them. So this will be then Ni over N0, just taking it from here, we have this is the P from the previous equation. So the P0 we obtain from here plus Nd. Okay? Now we multiply all the equation by N0 and we obtain a second order equation. Plus Na is equal to Ni 0 plus Nd. Okay, so this is a second order equation and we know how to solve this. So let's just write, okay, solve. You all know how to solve this. Solve. And we get that N0, this is a second order equation in N0, so we can solve for that. And we get Nd minus Na, okay, upon 2, we get plus minus square root of Nd minus Na squared over 4. Okay, plus the intrinsic concentration, okay, of impurities. So you see that now we obtain the whole, this is the full concentration of carriers in the conduction band, will be this function of the total density of impurities and this function of the intrinsic carrier concentration, okay? So we have a choice here of two signs, but only one of the signs will be physical, okay? Only one sign physical. Okay? So this sign, if we have, for example, if this limit, if Na and Nd equals to 0, then this is 0, this is 0. So if we choose the minus sign, we don't obtain the correct limit in which, where we have no dopants, so everything is intrinsic. So if choose plus sign only, we get correctly the limit N0 is equal to Ni. Okay, so we know that when we have no doping, okay, we only have the intrinsic concentration, okay, an intrinsic concentration of impurities, and also in what other limit? If we have the completely also, okay, also if complete compensation, so we have Na is equal to Nd, then we have also that N0 is equal to Ni. So you see that a completely compensated semiconductor is not very good because we only end up with a total concentration associated with the intrinsic carriers, which will be very low. So it's not convenient, okay? But you can sort of tune the action of the impurities by compensating, so you can lower or increase your concentration of impurities by manipulating the relative amount of donors and impurities. Okay, donor and acceptor impurities. Any questions here? Okay, so let's see one drawback of this relationship. Okay, one might think. Okay, let's see. One might think that, okay, that N0, okay, then is a combination of the intrinsic concentration plus the number of ionized donors, okay? this seems to be sort of trivial, right? I mean, you either have electrons from the intrinsic contribution or from the ionized donors, okay? But this turns out to be wrong. Okay, why? Because you can have this kind of thing, right? Let's suppose you have your conduction band, okay, and your valence band, okay? And then you have your impurity levels, your donor levels, for example. And let's suppose you have some intrinsic holes here, and you have some intrinsic electrons. So this would be this contribution here. But you see that not all the impurity electrons, okay, are going to go to the conduction band, but some impurity electrons may go down to the valence band. Okay, so this happens. We lose it. This electron no longer is going here, so this contribution is not precise. Okay, because this one is annihilating one of the intrinsic holes. That doesn't affect the number of electrons here, but this electron is no longer going to the conduction band. Okay, so this relationship would be wrong. Okay, the correct relationship is then, for example, here we have chosen the limit in which the number of acceptors, okay, is 0. Okay, so let's use the relationship we had before. So we have the total concentration, okay, is equal to, and this is not, we haven't made the assumption that all the impurities are ionized. So we have this is going to be P0 Nd minus N sub D plus Pa. Okay, if we have no acceptor impurities, this will be 0 also. Okay, so we have this relationship here. Okay, so the actual relationship will be P0. This will be Ni squared over N0 plus the total number of ionized impurities. Okay, so you see that this is the correct relationship here and not this one. Okay, so we have to be careful, okay, how we use the expressions. Okay, this implies, okay, assumes, okay, not even assuming that all the impurities are ionized, you get the correct relationship. You say this is a correct and this is wrong. Okay, okay, so be careful about using the expressions or making the wrong assumptions, because there are all these processes that we drew here. Remember, this is the full picture, okay? Full picture here. Full picture of what all the processes that can happen, okay? Here, we didn't even draw, okay, all the processes that can happen, and including these type of processes here that are taken into account. We don't miss these processes by taking into account the neutrality condition. Okay? Any questions about this? You have to make noise from time to time, otherwise I have to go back. Let's see if I can see you, whether you're here or not.
Yes, we do here.
Okay. Yes, we are here. Okay, good.
We are.
Yeah. Okay. Okay, so let me make now a picture which draws the full scenario. I'll draw two versions of this picture. Okay, so so we know what's happening as a function of temperature. Okay, so let me draw here the first one. Okay, so we have here. I haven't solved the orthogonality problem yet, but it's fine. And let me make a second plot here. Okay, so in this first plot, I'm going to draw here, and draw in blue, the total concentration of electrons in the conduction band, and I'm going to have here temperature. Okay, so we increase temperature in this direction. Okay, and let's draw some reference numbers. So we have, for example, 100. This can be 500 Kelvin, 700 Kelvin. Okay. So the curve is sort of let me use something that I was trying to learn how to do here. What did I do? This curve here. Okay. So at very low temperatures, you have you cannot even ionize the impurity levels. Okay, so you have now something like this. Okay, then you start increasing the temperature, you start ionizing. Okay, so but you're increasing the ionization of the impurities, and then you go to, you have ionized all the impurities, so you go to something like this. But at sufficiently high energies, temperatures, you will have that the intrinsic carriers increase a lot, okay, and you get something like this. Okay, so you see what's going on here. So how do we go back? How to write? Okay, so I go back to my pen. So here I would have a curve that's going like this. That's going to be the intrinsic. See how do I go back to writing the regular? Okay, so this would be the intrinsic. Jesus. This one? No, select. I don't really hear you very well. Here. See? No. So how do I undo this? Okay. Oh, I can't seem to go back to my pen here.
Maybe you should click again in the curve.
In the what?
In the curve, in the options up.
Options?
Yeah. You have activated the curve.
option. So just deactivated, right?
Yeah.
Okay. Okay, so this will be the intrinsic concentration. Thank you very much. Okay, so this will be the intrinsic concentration. That means that at very high temperatures, I can pay the price of electrons jumping the gap. So at very high temperatures, this will be an intrinsic system. Here on the other case, this will be the sort of the extrinsic range. Extrinsic range, okay? This will be the intrinsic range, very high temperatures. And of course, we have only a certain amount of impurities. So this is why this saturates. You ionize, okay? So this will be the partial ionization, okay? So at very low temperatures, here and here below, we have freezing of all. Okay, so we, of course, at very low temperatures, this should be an insulator of impurities. Okay, so at very low temperatures, you have no carriers at all. Then you increase the temperature, you start having carriers, and then you've ionized all the carriers. So you see that this will be the regime where the expression that we derived before is valid. So the extrinsic regime, all the impurities are ionized, so we have no more sources of impurities until at very high temperatures you start having a contribution from the intrinsic impurities, intrinsic electrons. Okay, so this will be remember that these will pay the price for the energy gap here. Okay, so that's the curve coming from that expression. Okay, and so this will be the full picture. Okay, another way that this is generally represented is, again, I have again the impurity concentration in the conduction band, and here we have the temperature. No, we have now we have 1000 over the temperature. Because remember that we have these inverse temperature relationships here. Okay, so in this case we have the intrinsic. Now we have low temperatures, so high temperatures are on this side of the axis in the top graph. The high temperatures are on the opposite side. So we have the intrinsic curve here, and we have something like this. Let me use again. So we have a curve going like this. Then we have the saturation range, and then we have the freezing range. Okay. So we have here we have the extrinsic regime. Extrinsic. Okay, this is the freezing of carriers, freezing, and this is the intrinsic regime. Okay, so they both curves say the same. Okay, this is basically just representing, this is high temperatures here, high temperatures, and low temperatures here. Okay. Okay, so this is the full scenario as a function of temperature. Okay, temperature dependence. Of a doped semiconductor. Okay, any questions about this? Okay, so I'll just write the corresponding relationship for the total density of positive charges in the valence band, okay, which you will have to derive in the homework. Here we just some very slight changes with respect to the formula we saw before. Again, we have to choose the plus sign here in order to obtain the correct limits. And we have here Na minus Nd over 2 plus the intrinsic carrier concentration. Okay, is this clear? Okay, what's the next topic here that we're going to treat? So we know now how to, one observation I want to make, you shouldn't use both formulas at the same time. That means that the formula, note. Okay, and this is a rather interesting observation. Okay, so you should not use both formulas. Okay, that is the formula for N0 and P0 at the same time. Okay, and this is a problem of error, or errors at the time of calculating things. Okay, you should use either the N0 formula and then P0 you calculate through the relationship P0 Ni equal over N0. Okay, you either use this, okay, or you know this, and then you calculate the N0 through the mass action formula. Okay, this is essentially because N0 is going to be very large. Okay, so this can be very large. Okay, so you can when you use both formulas, you're going to have two things of the same order of magnitude whose subtraction is going to be a very small number. So imagine that if you subtract two numbers that are 10 to the 16, you know, some number minus y 10 to the 16, okay? And you want to obtain some number that's order 10 to the 9, okay? So this is very difficult to do. You have to have a very high precision, or requires a very high precision, a large number of significant digits. Requires precision. Okay, so basically the idea is to use a formula for one of the concentrations and you obtain the other concentration by this relationship here. Okay, or you obtain the positive concentrations and then the other concentration you obtain it. Okay, because once you know this one, you should know the other one, and this saves you this error problem. Okay, this you might see in the lab, for example, when you do things in the lab. It's not advisable to use the formula from N0 and from P0 separately, but do use mass action always. Okay, this is just a practical matter. Of course, from the theoretical point of view, you don't need to do this because you have arbitrary precision. Okay, but if in the lab, in a practical scenario, this is the best way to go. Okay. Okay. Any questions? Okay.
No.
So yes. Okay. So let's finish the classes establishing another couple of relationships that are really important from the practical point of view. So we want to know now the Fermi energy, okay, as a function of impurity concentration. Okay, so what do we know? For example, we derived before, and remember this relation was general. Okay, we derived or that N0, that's the total density of electrons, okay, in the conduction band, was the see, 1 second, definition here. So we had this relationship before. So 1 minus beta E conduction minus EF. Remember that this relationship was general because we are not assuming that this is the intrinsic Fermi level, but the doped. So this would be the doped Fermi level, okay? And the Fermi level that is calculated also taking into account differences in the densities of states of the conduction and the valence band, okay? So this is general, because we get all the information about the impurities should be inside here. So we're now going to solve for the Fermi energy starting from this relationship. So this is the total concentration of electrons in the conduction band. Remember that this is the effective okay, density of states of the conduction band. Okay, that's very important. Okay, so now we can solve for and there's an also, okay, again, and I'm always going to make this a rule of telling you that, okay, what approximation. So this is a Maxwell-Boltzmann approximation. But we're going to use this all the time. You'll see one exercise in the homework will tell you that the deviations from this approximation, if you take the full Dirac Fermi-Dirac distribution function, the deviations from this Maxwell-Boltzmann are going to be really small. Okay, so we solve. Okay, we take the logs on both sides, and we end up with this relationship here. So the energy of the conduction band minus the energy of the Fermi level is kBT log of the effective density of states over N0. Okay, so once we know the concentration of electrons in the conduction band, then we know the relationship, okay, the relationship between the Fermi level and the bottom of the conduction band, okay? So let's see, if we have lots of electrons here, okay, so this ratio is going to get reduced, so the Fermi energy approaches the conduction band, the bottom of the conduction band. So you see that's the logic of this formula. So if N0 increases, this is fixed. This is fixed by the band structures. Okay, so this is fixed by band structure. Okay, so if we increase this by doping, for example, then we see that this gets smaller because the log is monotone with its argument. And then this is going to get smaller. So this Fermi energy is going to get closer to the conduction band. So you see that just here in a small diagram here. So if we start with an intrinsic concentration, okay. So we have here the Fermi level, intrinsic Fermi level, okay? So if we have lots of electrons now here, okay? So this Fermi level is going to go up towards the conduction band. So we're going to have a Fermi level that's going to be here. Okay, on the other hand, if you reduce the carrier concentration at the top, okay, so this gets smaller, this gets larger, this is monotone with the log, so this gets larger, and the Fermi level in the conduction band get more separated. So we get a motion in the opposite sense. Okay. So this makes all the logic in the world. So if we have if we have a n-type, okay. So let's suppose we have an n-type. If n-type semiconductor, okay. What happens if the number of dopants, okay, the doping atoms, is much larger than the intrinsic, the concentration of dopant atoms is much larger than the concentration, the intrinsic concentration of electrons, okay? So if we take the formula for the density of carriers in the conduction band, so this would be Na over 2 plus square root Nv minus Na squared over 4 plus Ni. I have a mistake here in my notes. So if it's an n-type, okay, an n-type implies that Nd is much larger than Na, okay, if it's an n-type. So you can show that then this is much larger than this. So we just left with Nd squared over 4, and then Nd over 4 is much larger than the intrinsic concentration. So you get that this is just the number of donor atoms. Okay, so just take this limit, and d is much larger than I, so we can neglect this one in front of this term here, and here this neglect this one in this number of acceptors or concentration of acceptors in front of the concentration of donors, and we get just the concentration of donor atoms in the problem. Okay. So one approximation, in this approximation, we would have that the formula we can write, the previous formula, we can write as EZ minus EF is equal to KBT log of the total density, the density of states in the conduction band divided by ND. Okay, this is when ND is much larger than NA and N sub I. Okay? This limit, okay, in case, okay, in the case, we would also obtain this kind of a limit if, let's suppose that NA, ND minus NA is much larger than Ni, then we would have that N0, okay, from the previous formula is approximately equal to Na minus Nd minus Na, okay? Okay, so this you can see from the previous formula, right? So you just have Nd, this you leave alone, and this you neglect Ni in front of this term, so you eliminate this intrinsic concentration. The square root of this gives you another factor of 1/2, and then you get this formula here. Okay. What other final relationship can we see here? Okay, so remember we also saw another version of the formula for the total concentration. Okay, let me just put what I'm going to do here. So, okay, another useful relationship is that we had a relationship where we related the total concentration and we put it in terms of the intrinsic concentration, but this was a function. The exponent was EF minus EFI. So this is also measuring now. We're measuring the distance between the Fermi level with impurities as compared to the Fermi level without impurity. Okay? So from here, taking logs on both sides, you get that this difference, okay, is going to be KBT times the log of N0 over Ni. So you see now, when you compare the total concentration with the intrinsic concentration, this is a ratio that's going to give you the relative distance between the intrinsic Fermi level and the actual Fermi level. Okay, if you see that all the concentration of impurities are coming from, okay, if this is one useful limit to check. So if N0 is the intrinsic concentration, that is, we have an intrinsic semiconductor. So this will be either an undoped system or or the system at very high energy, very high temperatures. Then this is 1, the log of 1 is 0, and we have that EF is equal to the intrinsic concentration. Okay? And finally, likewise, we have all the, okay, likewise, we have all the same relationships for the positive. We have, okay, we can start from the total density of states. This will be the total concentration of holes in the valence band. We have E to the minus EF minus EV, okay? And this implies that the distance between the Fermi energy and the top of the valence band is going to be KBT log of the density of states in the valence band divided by the total concentration of holes in the valence band. Okay. Okay, so I think we've already passed the time. Okay, so this is all the relationships I wanted to show you for equilibrium semiconductors. Okay, equilibrium semiconductors. We finished this chapter completely. Semiconductors. And next class, you're going to see, next class, okay, you see carrier transport. Okay, you see that I'm following this book, Neamen. Okay, so please, if you have any you want to revise the material, it's going to be there. Okay, most of the material, the other part of the material that we're not covering, or we're not explicitly covering in class, are going to be part of the problems, or part of the problem sessions in the class. But I thought it would be useful, especially under the circumstances we are now, to have you follow, let us follow a book instead of just giving you a totally different material, so that you can check the book or ask questions in the recitation or ask me questions through the email. Okay, so next class, carrier transport. So you're going to be calculating electron and hole currents, okay, in these systems. Any questions? We have to hurry to the next class, I guess. Okay, so we stop here. Okay, thank you. Okay, see you next class.
Bye, teacher.
See you.
Bye.
No han comido, pero